Chapter 3, we will be looking at matter and energy and the properties related to those. We want to start by looking at the idea of atoms and molecules. So remember that we said everything around us is made up of chemicals. Well, going a little bit further than that, everything that you can see in the room around you is made of matter. And different kinds of matter are related to the differences between the molecules and atoms that make up that matter. So the different properties of an atom or a molecule will determine the properties of the matter around you. So for example, if you look at the diagram shown here, on the left they're showing a blow-up of water molecules in a water bottle. And on the right, they're showing the structure of carbon atoms in graphite in a pencil in the figure to the right. So when we're talking about matter, we're talking about substances in chemistry, we're talking about anything that occupies space and has a mass. We can weigh it. So some types of matter are easily visible to our eyes, but there are other types of matter such as air, microscopic dust, things of this nature that are matter. They're there, they occupy space, they have mass, but we can't see them without magnification. We can sense them in other ways. We can sense the wind blowing around us, or if you get that dust up your nose and it makes you sneeze, but you can't just see it outright without some help. Now, some matter may appear to be perfectly smooth and continuous, but in reality, no matter is perfectly smooth. It's just a matter of perspective. It's ultimately going to be composed of atoms, these little sub-microscopic particles that are our fundamental building blocks. Everything's made up of those. And the atoms can be bonded together in different ways to form molecules. Molecules will be joined in specific geometric arrangements. And the amazing thing, we alluded to this in our earlier chapter, but there are many recent advances in microscopy that allow us to actually see, to image those atoms and molecules rather than just imagining them. And we'll take a look at those in a minute, but let's just kind of look at atoms and molecules. So all matter is ultimately composed of atoms. In some substances, such as the aluminum in this aluminum soda can, the atoms exist as independent particles, and they're just stacked together in a neat arrangement. In others, if we look, for instance, at the figure on the right of the isopropyl alcohol, you will have several atoms bonded together to make a well-defined structure called a molecule. So if we look at this rubbing alcohol, we've got carbons, we've got hydrogens, we've got oxygens. The carbons are the black, the hydrogens are the white, the oxygen are the red. And then those together, all those molecules come together to make this liquid form that we know as isopropyl or rubbing alcohol. Now, this is a very interesting image right here. This is actually a scanning tunneling microscope image of nickel atoms. And the scanning tunneling microscope is really interesting. It creates an image by basically taking a stylus or a tip of atomic dimensions, very, very submicroscopic point, and it runs it over the surface and creates an image by scanning over that surface, and it can actually distinguish individual atoms. So in this figure, all the little blue bumps that you're seeing are individual nickel atoms coming together to make up a piece of nickel. Here's another one. This one is really fascinating. This is a scanning tunneling microscope image of a DNA molecule. And if we look here, the DNA molecule is represented in yellow, and you can actually make out the double strand helix, the double helix that makes up the DNA. So you can see a strand here, you can see a strand right here, and you can see them intertwining. And this is amazing that we're actually able to see the individual atoms here and the structure that it makes up. So pretty amazing advances here. Now, a lot of this chapter is pretty common sense stuff, but we just need to run through it just to be sure everybody's on the same page here. So, we know the three common states of matter. We've got solid, liquid, and gas, where solid is going to be defined as a substance in which the molecules are very closely spaced. Now, that does not mean that there's no motion in a solid. The molecules in a solid are actually vibrating around a fixed point, but that's all they can do really, is just kind of vibrate. They can't move around freely, and so generally they're not moving relative to one another. So our example here is if we look at, we're looking at H2O and all of these examples, that in the solid form, all of these little H2O molecules are packed together, and they can vibrate around the point within the molecule, but there's no room for them to vibrate freely and move about. Okay, now we move to the liquid phase. So we warm it up, we end up with the liquid, and now we can still see the individual H2O molecules. They're still fairly close together, but they have enough space to kind of slip past one another and move around, and gives it a little more degree of freedom, so that now if I didn't have a container around this, it would just spread out to fill, whatever space is available to it. So it's going to still, against gravity, but it's going to spread out in that container. And then as we continue heating it, we move on to the gaseous phase, which is steam. This is where there's enough energy in each of these individual molecules that they can break apart. They have freedom of movement. There's a lot of distance between each molecule. They don't have to significantly interact with one another. They can simply move about as space provides. Okay, so solid, liquid, and gas. I want to take a second just to point out a little bit of a difference in some different types of solids. So when you're talking about solids, you can either have crystalline solids, as shown in the figure on the left, where the atoms and the molecules are arranged in a very structured, orderly pattern, and there's not a lot of room for movement among those, but you see this repeating pattern over and over again. And then you can also have amorphous solids. So in this case, for instance, they're showing glass, where you have the same sorts of atoms and molecules, and you can roughly see something similar excuse me, but you can see that there's not that rigid repeating pattern. There's sort of a sense of willy-nilly about it, so they're not arranged neatly. No long-range order. Just some examples of the two of those. Table salt, sodium chloride, is a very crystalline, structured material. We're used to seeing crystals of salt. And if we could look at that on the molecular level, we would see that we have individual atoms of sodium, the purple, and chlorine in the green, arranged in a neat, orderly fashion to make this little cube. You're probably familiar with diamonds. Those are crystalline solids. Other crystals that you may think of, galena, which is lead sulfide. We've got quartz, silicon dioxide. We've got pyrite, which is iron sulfide. Okay, very neat crystalline arrangements. And then amorphous solids, we have things such as glass, both the glass that we're familiar with for both art and function in our buildings, and also this is a natural glass. It's a piece of obsidian that came from a volcano. Rubber is an amorphous solid, so the rubber that we have in tires, rubber gloves, rubber ducks, those are all amorphous solids. And many different types of plastic. So these are just little plastic beads, but anything you have that's made of plastic, that's an amorphous solid. There's not a long-range rigid structure to it, so it gives it some flexibility. And just a reminder on gases. Property interesting to gases that we will be looking at later. Remember that gases are compressible. So when we look at a solid, the atoms are already about as close together as we're going to get them. So if we put them in a container and applied pressure to them, that solid's not going to get a lot smaller. It's only going to, if you have airspace in there, you can break something apart and remove that airspace, but the solid itself, if you had a sheet of metal, you're probably not going to be able to compress that very much. If you have a gas, you can put pressure on that. If you have a syringe and you seal it up and you push down on that, you can compress that gas to a certain extent. You can press it to the point, if you have enough pressure, until the molecules come together enough to become a liquid or perhaps even a solid. So remember that gases are compressible. So just a summary of the properties of liquids, solids, and gases. Remember that on the atomic level, solids can oscillate or vibrate around a fixed point, but not a lot of movement. Liquids are free to move relative to the molecules within them to one another, and gases are free to move about freely within a container. The spacing of atoms or molecules in solids and liquids tend to be fairly close together. Gases, they're spread far apart. Solids have a definite shape, whereas liquids and gases are indefinite. They take on the shape of their container. As far as volume goes, a solid and a liquid have a definite volume. So you can measure that volume. That's going to be a fixed amount. A gas is an indefinite volume. A gas will expand to fill the volume of whatever container it's in. Solids and liquids, not compressible. Gases are going to be compressible. Okay, so that's your summary for solids, liquids, and gases. In the next section, we'll look at the idea of elements, compounds, mixtures.